For most of human history, the word planet carried a promise of ground beneath your feet, of skies above your head, of places where life could at least in principle exist. When astronomers first began discovering planets beyond our solar system, many believed we were standing at the edge of a revelation. Thousands of new worlds awaited us, hidden in the dark between the stars. Surely among them there would be oceans, continents, perhaps even distant Earths staring back at us, but the universe had other plans. The first exoplanets we found were not gentle worlds, they were nightmares. Planets larger than Jupiter orbiting closer to their stars than Mercury ever could. Worlds heated to thousands of degrees where metal vaporizes and rock flows like water. Planets crushed by gravity so intense that atoms themselves are forced into unfamiliar arrangements. Worlds where winds scream faster than sound, carrying storms of molten glass or iron rain. These were not havens for life, they were warnings. At first, astronomers assumed this was a bias in our instruments. We were simply detecting the easiest planets to find, the biggest, the hottest, the most extreme. Surely calmer worlds existed further out, hidden beyond our reach. But as technology improved, the picture did not soften, it sharpened. With every new telescope, every new survey, the same pattern emerged. The galaxy is not filled with Earth-like worlds quietly waiting for discovery. It is filled with extremes. The phrase uninhabitable world stopped being an exception. It became the rule, and that forces a difficult question. If planets like Earth are rare, if most worlds are hostile to life as we know it, what does that say about our place in the universe? To understand this, we need to abandon a comforting illusion. The illusion that the universe is designed with us in mind. Earth feels natural to us because we evolved here. Its temperature range feels reasonable because our biology depends on it. Its atmosphere feels breathable because we are adapted to it. But these conditions are not universal standards. They are accidents. The universe does not prefer liquid water on the surface of a rocky planet. It does not prefer moderate climates or calm stars. It does not prefer stability. The universe prefers energy, and energy left unchecked creates extremes. Most stars in the galaxy are red dwarfs, small, cool, and violent. They flare unpredictably, blasting nearby planets with radiation capable of stripping atmospheres entirely. Many planetary systems migrate over time, dragging worlds inward toward stellar infernos or flinging them into frozen darkness. Even within our own solar system, Earth is an outlier. Venus likely once had oceans. Mars once had rivers. Both lost their habitability not through catastrophe, but through slow, inevitable processes. Venus succumbed to a runaway greenhouse effect, turning its oceans into steam and its skies into acid. Mars lost its magnetic field, allowing the solar wind to peel its atmosphere away atom by atom. These are not rare tragedies. They are common outcomes. When we look at exoplanets, we are not seeing alien oddities, we are seeing the natural consequences of planetary physics played out across billions of years. Consider lava worlds. These planets orbit so close to their stars that solid ground cannot exist on their daysides. Temperatures soar beyond 2000 degrees Celsius. Rock melts. Oceans, if they ever existed, vanish completely. Some lava worlds are tidally locked, forever showing one face to their star. One hemisphere becomes a glowing sea of magma, the other may be locked in eternal night. This is not science fiction. These worlds are real, detected through precise measurements of starlight and heat. Or consider ultra-dense planets, sometimes called super-Earths, though the name is misleading. Some have masses several times that of Earth, compressing their interiors under crushing pressure. On these worlds, mountains may collapse under their own weight. Atmospheres, if present, may be hundreds of times thicker than ours. Then there are gas giants orbiting impossibly close to their stars, hot Jupiters. Worlds with no solid surface at all, where temperatures vary wildly and storms rage without end. In their atmospheres, exotic chemistry unfolds. Clouds of vaporized rock, rain made of molten metals, winds faster than any hurricane imaginable. And yet none of this is abnormal. What is abnormal is Earth. Earth sits in a narrow window where water can exist as liquid on the surface for billions of years. Its orbit is unusually circular, its star unusually calm. its magnetic field unusually strong. Even small deviations from these conditions can push a planet into one extreme or another. This realization marks the beginning of a deeper conflict. For decades, the search for life focused on finding Earth 2.0, a twin world with familiar conditions waiting for us to recognize it. But the universe does not seem eager to provide such twins. Instead, it offers diversity without comfort. The more planets we discover, the clearer it becomes that habitability is not a default state. It is a temporary balance, a fragile one, easily disrupted by stellar evolution, orbital shifts, or internal planetary changes. This reframes the entire search for life. Instead of asking which planets are like Earth, we are forced to ask, how does life survive when planets are nothing like Earth? And that question leads us down a far more unsettling path. Because if most worlds are extreme, then life, if it exists elsewhere, must be extreme as well. It must adapt to heat, pressure, radiation, and chemical environments that would destroy us instantly. It must find energy not from sunlight and gentle climates, but from gradients, chemistry, and internal heat. The universe, it seems, does not care whether a planet is comfortable. It only cares whether energy flows. And wherever energy flows, complexity can arise. The hook is no longer the hope of finding another Earth. The hook is the realization that Earth may be one of the rarest outcomes of planetary evolution, not because life is special, but because stability is. As we move deeper into the catalog of uninhabitable worlds, the question will stop being whether life can exist there. The question will become far more uncomfortable. What kind of life could survive a universe like this? And what does that mean for us? A species balanced on a narrow ledge of habitability, living on a planet that may be far more fragile than we ever wanted to believe. As astronomers pushed deeper into the exoplanet catalog, something unsettling became clear. The more worlds we discovered, the less familiar the universe became, not gradually, abruptly. Planets did not line up neatly along expectations formed by our solar system. Instead of orderly orbits and predictable categories, we found chaos, migration, and extremes stacked upon extremes. One of the first shocks came from hot Jupiters, gas giants larger than Jupiter orbiting their stars in just a few days. Worlds so close that their atmospheres are heated to thousands of degrees, expanding outward like bloated balloons. According to early models of planetary formation, these planets should not exist. Gas giants are supposed to form far from their stars, ice and gas can accumulate. And yet there they were. The only explanation was migration. These planets were born far away and then dragged inward, destabilizing everything in their path. Any smaller worlds unlucky enough to share their system were likely ejected, shattered, or consumed. This was our first warning that planetary systems are not gentle places. Then came the super-Earths. These planets occupy a mass range between Earth and Neptune. Some are rocky, some gaseous, some something in between. Their diversity is staggering. On many of these worlds, gravity would be 2, 3, even 5 times stronger than Earth's. An atmosphere, if present, would be compressed into dense layers. Weather systems would behave differently. Mountains might not rise at all, collapsing under their own weight. And yet super-Earths are among the most common planets in the galaxy. This forces a difficult realization. Our solar system is not typical. For a long time, we assumed our planetary layout was normal. Small rocky planets close in, gas giants further out. But statistically, we are an exception. Most planetary systems look nothing like ours. They are more compact, more chaotic, more violent. Then there are the tidally locked worlds. Planets orbiting close to small stars often become locked, showing the same face to their sun forever. One hemisphere experiences eternal daylight, the other eternal night. On the day side, temperatures may reach extremes capable of melting rock. On the night side, temperatures may plunge so low that atmospheres freeze and collapse. At first glance, these worlds seem completely hostile, but climate models complicate the picture. If a planet has a thick enough atmosphere, heat can be redistributed. Powerful winds could transport energy from day to night. In some cases, a narrow band around the terminator, The line between light and dark could remain relatively stable. Habitability, if it exists at all, would not be global, it would be localized. Life clinging to edges, then come the iron worlds. Planets so close to their stars that lighter materials were stripped away, leaving behind metal-rich cores. On these worlds, iron may dominate the surface. Lava oceans could consist not of silicates, but of molten metal. The magnetic environments of such planets would be extreme. Electrical currents induced by stellar interaction could be immense. Auroras would not be gentle lights in the sky, but planet-wide electrical storms. These are not environments where forests grow or oceans teem with fish, but they are environments where energy flows intensely, and energy is the currency of complexity. Some exoplanets take this even further. Ultra-hot Neptunes and mini-Neptunes with atmospheres so heated that molecules are ripped apart. Hydrogen escapes into space, leaving behind heavier elements. These planets are literally evaporating. We are watching them die in real time. And this reveals another uncomfortable truth. Planets are not static objects. They are processes. Atmospheres evolve. Surfaces transform. Orbits shift. Habitability is not something a planet either has or does not have. It is something it may pass through, briefly, before moving on. This leads us to planets with glass ring. On worlds like HD 189733b, temperatures are so high that silicate particles form in the atmosphere. These particles condense into droplets of molten glass. Carried by winds exceeding 5,000 kilometers per hour, they fall sideways, scouring the skies. This is not metaphor, this is physics. Spectroscopy confirms the presence of silicates. Atmospheric models explain the dynamics. These planets exist in a perpetual state of violence, and yet they are stable. This is where the rising action intensifies, because stability does not require gentleness. It requires balance, even if that balance is brutal. The universe appears to favor systems that endure extremes rather than avoid them, which raises a disturbing implication. If most planets are extreme, and if stability can exist within those extremes, then life elsewhere may be adapted to conditions we would label catastrophic. Life may not need oceans on the surface. It may thrive underground, shielded from radiation. It may use solvents other than water. It may metabolize chemicals we consider toxic. Our definition of uninhabitable begins to collapse, not because these worlds are suddenly friendly, but because life is more flexible than comfort. But here the conflict sharpens. Complex life requires time. It requires long periods without global resets. It requires environments that allow information to accumulate. Extreme worlds may allow life to exist, but they may prevent it from advancing. A planet constantly reshaped by stellar flares, atmospheric loss, or orbital instability may never allow ecosystems to mature. Evolution could be trapped in survival mode. This may be why microbial life could be common, while technological civilizations are rare. The universe may be full of life that never gets the chance to become anything more, and that reframes the meaning of uninhabitable worlds yet again. They are not simply hostile environments, they are filters. Filters that test whether life can endure. Filters that decide whether complexity survives. Filters that determine whether intelligence ever has time to emerge. As we catalog more and more extreme planets, the pattern becomes impossible to ignore. The galaxy is not optimized for beings like us. We are optimized for a narrow, fragile window that may close without warning. This is not pessimism, it is context, because understanding how rare stability truly is forces us to reconsider our assumptions about destiny. If Earth-like conditions are fleeting, if most worlds never experience them at all, then intelligence may not be the natural outcome of life. It may be an anomaly, and that realization sets the stage for the next escalation, because some of the most extreme worlds we know are not planets at all. They are moons, and those moons may quietly undermine everything we think we know about where life can survive. At some point, the narrative of extreme planets reaches a breaking point, because if worlds of fire, pressure, radiation, and chaos are the norm, then we are forced to confront an uncomfortable contradiction. Life is resilient, but intelligence is fragile. This is where the true conflict begins. For years, scientists took comfort in extremophiles on Earth, microbes living in boiling vents, bacteria thriving beneath ice sheets, organisms surviving radiation, acid, and crushing pressure. These discoveries expanded our imagination. They suggested that life could exist almost anywhere. But survival is not the same as progress. A bacterium living near a hydrothermal vent can persist for billions of years without ever changing in meaningful complexity. Evolution keeps it alive, not ambitious. Complex life requires more than endurance. It requires stability long enough for ecosystems to layer, diversify, and specialize. It requires environments that are harsh enough to drive adaptation, but calm enough to avoid constant reset. And when we examine the most extreme exoplanets, that balance often seems absent. Take planets orbiting red dwarf stars. These stars are small, cool, and long-lived. On paper, ideal hosts for life. They can burn for trillions of years, far longer than stars like our Sun. But they are violent. Young red dwarfs unleash powerful flares and coronal mass ejections. A planet in the habitable zone must orbit extremely close, often closer than Mercury is to the Sun. At that distance, radiation bombardment is relentless. Atmospheres are stripped away, oceans evaporate, surface conditions oscillate wildly. Even if life emerges early, it may be forced underground, beneath oceans, or into chemical niches isolated from the surface. And here the conflict sharpens. Subsurface life may survive, but it may never see the stars. Photosynthesis, one of the great engines of complexity on Earth, depends on surface light. Without it, energy budgets shrink, ecosystems simplify. A planet filled with microbial life beneath kilometers of ice may be biologically rich, but technologically silent. Then there are ocean worlds, planets entirely covered by global oceans hundreds of kilometers deep. No continents, no exposed land, no shallow waters cycling nutrients between rock and air. At first, these worlds sound promising. Water, abundant, temperatures may be stable, but geology matters. On Earth, plate tectonics recycle carbon, regulate climate, and create chemical gradients that life exploits. On ocean worlds, high-pressure ice may form at the bottom of the ocean, sealing the water from the rocky mantle below. Without contact between water and rock, key chemical cycles stall. Life may appear, but complexity may plateau. And then there are worlds in constant transition, planets migrating inward toward their stars. Planets losing atmospheres faster than biology can adapt, planets experiencing extreme obliquity shifts, plunging from ice ages to infernos in geological moments. Evolution thrives on challenge, but it dies under instability. This reveals the core tension of the universe. The same forces that create diversity also destroy continuity. Energy drives chemistry, chemistry drives life, but energy, unchecked, destabilizes environments. The universe does not optimize for long-term habitability, it optimizes for change. Even Earth has not been spared. Our planet has endured mass extinctions that wiped out the majority of species alive at the time. Asteroid impacts, volcanic winters, runaway climate shifts. Each time, life recovered, but intelligence nearly didn't. If the asteroid that killed the dinosaurs had arrived a few million years earlier or later, human evolution might never have happened. And Earth is one of the calmer worlds. Now imagine these same processes on planets already living on the edge. The conflict becomes unavoidable. The universe may be excellent at creating life, but it may be terrible at preserving the conditions needed for intelligence. This leads to a darker interpretation of uninhabitable worlds. They are not failed Earths. They are successful planets that followed physics to its natural conclusion. They reveal that habitability is not a destination. It is a temporary alignment of factors that rarely lasts. This realization feeds directly into one of the most unsettling ideas in modern astronomy, the Great Filter. The hypothesis that somewhere between simple life and advanced civilization lies a barrier so difficult to cross that almost nothing survives it. Extreme planets offer many candidates for that filter: atmospheric loss, stellar violence, orbital chaos, runaway greenhouse effects, loss of magnetic fields. Each of these can quietly erase billions of years of progress. No explosions, no warnings, just gradual uninhabitability. And this is where the emotional weight of uninhabitable worlds truly lands. They are not just distant curiosities, they are alternate futures. Venus may once have been Earth-like, Mars may once have had rivers and lakes. Something went wrong, or simply continued. The line between habitable and uninhabitable is not sharp. It is thin and unstable, which forces us to confront an uncomfortable truth. Earth is not safe by default. Our planet remains habitable, not because it must, but because it has not yet failed. The conflict deepens further when we consider time. Stars evolve, luminosity increases, habitable zones move outward. In a few 100 million years, Earth will begin to heat beyond comfort. In a billion, oceans may evaporate. In a few billion, life as we know it will end. Even perfect stability is temporary. So, when we look at uninhabitable worlds, we are not just seeing alien hellscapes, we are seeing inevitability. This reframes the central question once again. The question is not whether planets can host life. They clearly can. The question is whether intelligence can outrun planetary destiny. Can a species recognize the fragility of its environment and time? Can it adapt faster than stars evolve? Can it escape surface dependence before surfaces become lethal? Uninhabitable worlds suggest that most do not. They imply that the universe may be full of life that never escapes its cradle. Life that survives, adapts, and endures, but never reaches outward. Civilizations may be rare not because intelligence is hard, but because time is short. This is the conflict at the heart of the story. The universe offers countless worlds, but very few chances. And every extreme planet we discover tightens that tension. Because somewhere in the catalog of lava oceans, glass storms, frozen gents, and evaporating atmospheres lies a silent message. Life is persistent, but habitability is fragile. And intelligence, if it hopes to last, must learn this lesson faster than evolution ever did. Just when the picture seems almost hopeless, the universe offers a quiet reversal, not a miracle, not salvation, but a reminder that life has never played by our rules. Because while the surfaces of many worlds are hostile, violent, and unstable, planets are not only their surfaces. For decades, habitability was defined by what we could easily imagine: oceans under open skies, sunlight driving ecosystems, climates resembling our own. But this was never a scientific necessity. It was a limitation of perspective. The comeback begins beneath the surface, in our own solar system. Some of the most promising environments for life are hidden far from sunlight. Europa, a moon of Jupiter, hides a global ocean beneath tens of kilometers of ice. Enceladus, orbiting Saturn, sprays plumes of water vapor into space, water that comes from a warm ocean beneath its frozen crust. Titan hosts complex organic chemistry under an orange haze, with lakes not of water, but of liquid hydrocarbons. These worlds were once dismissed as frozen wastelands. Now they are central to the search for life. The lesson is profound. Surface habitability may be rare. Subsurface habitability may be common. Beneath ice, radiation becomes irrelevant. Temperature stabilizes. Water, if present, can persist for billions of years. Energy does not come from stars, but from within. Tidal forces generated by giant planets need their moons, creating heat through friction. Radioactive decay warms interiors. Chemical reactions between rock and water produce energy gradients life can exploit. This is not speculation. On Earth, entire ecosystems thrive around hydrothermal vents, completely independent of sunlight. They feed on chemistry, not photons. If such environments exist here, there is no physical law preventing them elsewhere. And when we extend this logic to exoplanets, the implications are staggering. Many planets classified as uninhabitable may still host internal oceans, ice-covered super-Earths, rogue planets drifting through interstellar space, warmed from within, moons orbiting gas giants far outside traditional habitable zones. These worlds would be invisible to surface-based definitions of life. They would not glow with biosignatures in their atmospheres. They would not signal their presence. They would be quiet. This changes everything, because it means the universe may be filled with life that does not announce itself. Life that never alters a planet's atmosphere in obvious ways. Life that never builds cities or transmits radio waves. Life that persists in isolation, deep beneath protective layers of ice or rock. From an astronomical perspective, such life might as well not exist. But from a biological perspective, it could be widespread. The comeback continues when we revisit worlds we thought we understood. Tidally locked planets, once considered hopeless, begin to look more nuanced. If a planet retains a thick atmosphere or deep ocean, heat can be redistributed. The day side may be brutal, the night side frozen, but between them lies a twilight zone, a permanent band of moderate conditions. Life does not need global habitability. It needs refuges, even red dwarf systems, once written off due to stellar violence, may offer shelter. A planet with a strong magnetic field or a dense atmosphere could shield its surface. Subsurface environments would be largely unaffected by stellar flares. The universe does not offer perfection, it offers niches. This realization reframes the conflict entirely. Extreme worlds do not eliminate the possibility of life. They constrain where life can exist and how visible it becomes. And visibility, it turns out, may be the real bottleneck. Life that remains underground leaves no atmospheric signature, no oxygen spikes, no methane cycles easily detected across light years. Civilizations that never reach the surface or never rely on large-scale energy use may remain permanently hidden. This suggests a quiet universe, not because life is rare, but because it is subtle. But the comeback does not stop at biology. Extreme chemistry opens doors we once considered impossible. On Titan, complex organic molecules form in cold, hydrocarbon-rich environments. These molecules assemble without liquid water. They demonstrate that prebiotic chemistry is not limited to Earth-like conditions. On high-pressure worlds, exotic forms of ice behave like rock, conducting heat and electricity. In such environments, unfamiliar forms of metabolism may emerge, driven by gradients we barely understand. The universe experiments constantly. Carbon-based life in water be only one expression among many. This does not mean intelligence is common, but it does mean life is stubborn. And this leads to a crucial reframing. Perhaps uninhabitable worlds are not failures of life, but barriers to complexity. Perhaps the universe produces life easily, but hides it effectively. The comeback, then, is not optimism, it is humility. We realize that our instruments are tuned to find versions of ourselves. Oxygen-rich atmospheres, surface oceans, industrial signatures. But the universe may be filled with living worlds that never match our expectations. Worlds where life persists quietly for billions of years without ever triggering a detectable signal. Worlds that are biologically rich and astronomically silent. This resolves part of the conflict. The absence of evidence is not evidence of absence. It may simply reflect the fact that most life does not advertise itself. And this has a final, unsettling implication. If life elsewhere tends to retreat inward, underground, underwater, beneath ice, then intelligence may face a choice, either remain hidden and endure, or become visible and risk instability. Extreme worlds may not prevent intelligence from arising. They may discourage it from expanding. The comeback is subtle, but powerful. The universe is not barren, it is cautious, and in that caution lies a lesson. Survival does not require comfort, it requires adaptation. As we continue cataloging uninhabitable worlds, the narrative shifts once again. They are no longer symbols of failure. They are demonstrations of how far life can bend without breaking. And that sets the stage for the next escalation. Because if life can survive almost anywhere, but intelligence struggles to last, then the most extreme environments may shape not just biology, but the future behavior of civilizations themselves. The realization that life may exist beneath ice, oceans, and rock does not end the story. It changes its stakes. Because once life finds a way to survive in extremes, the next question is inevitable. Can it evolve beyond survival? Can intelligence emerge in worlds that seem uninhabitable from our perspective? We begin to see that the universe has constructed a hierarchy of challenge. Planets exposed to violent flares, tidal forces, molten surfaces, or crushing gravity may still host life, but that life faces constant pressure to adapt. Microbes may evolve enzymes resistant to high temperatures. Photosynthetic organisms may capture energy from faint light or chemical gradients. Life may become more efficient, more robust, more ingenious in exploiting every narrow opportunity. Extreme environments are laboratories of evolution, and the consequences of these laboratories ripple outward. Consider the possible adaptations of life on a tidally locked world. One hemisphere scorched by constant light, the other a frozen abyss. Organisms might cluster in the twilight band, developing behaviors and morphologies perfectly suited to gradients of temperature and light. They might exploit convection currents, chemical fluxes, and thermal vents in ways we cannot yet imagine. The stakes rise further when we examine planets with glass rains or iron showers. Life would have to endure violent winds, corrosive precipitation, and surfaces that literally flow like molten metal. Survival might depend on mobility, protection, or biochemical resilience beyond anything on Earth. The rules of life are rewritten, and yet, evolution could find its path. Energy gradients exist even in the harshest environments. Chemical disequilibria are present everywhere. Where there is energy, there is potential for complexity. This is where the rising action intensifies. If life adapts to extremes, the narrative of Uninhabitable Worlds transforms. From a story of hopelessness to a story of opportunity, the very forces that seem destructive become engines of innovation. Survival pressures may sculpt organisms capable of astonishing feats: endurance, efficiency, intelligence. Some scientists have begun to speculate that technological life, if it emerges, may be even more likely to arise under these extreme pressures. A species surviving tidal heating, extreme radiation, or fluctuating atmospheres would have to be exceptionally adaptable, exceptionally observant, exceptionally cooperative. Perhaps the very rarity of stable surfaces accelerates ingenuity, rather than suppressing it, and this leads to another layer of revelation. Extreme planets are laboratories not just for life, but for the potential paths of civilization. Consider planets with violent orbital dynamics, regular comet impacts, atmospheric stripping, or orbital instabilities may periodically reset ecosystems. Life on these worlds must respond quickly. Memory, culture, technology, if they exist, must be robust enough to survive abrupt disruptions. Civilizations in such contexts may be cautious, precise, long-term thinkers, mastering adaptation as much as ambition. This is a universe where survival is synonymous with foresight. The pattern becomes even more compelling when we consider moons orbiting gas giants. These worlds are shielded from some stellar extremes, but exposed to others. Tidal flexing, radiation belts, and magnetospheric currents, yet tidal heating ensures liquid water, chemical cycling, and energy gradients. A moon in a planet's orbit may be more hospitable to life than a planet exposed directly to stellar chaos. Life finds its niches in unexpected places, and that brings us back to Earth. When we study extreme exoplanets, we are simultaneously studying the fragility and uniqueness of our own world. Earth's stability may have been essential not only for life, but for the evolution of intelligence capable of observing the universe. This lends a humbling perspective. Our civilization is a product of an extraordinarily narrow window of planetary conditions that may be exceedingly rare in the cosmos. But, as we map these extremes, a tentative pattern emerges. Life is everywhere that energy flows. Intelligence, by contrast, may be rarer, but not impossible. It may arise where life is forced to adapt to extremes, where stability is intermittent but persistent, and where pressures forge ingenuity. From a cosmic perspective, the narrative arc shifts. Uninhabitable worlds are no longer only cautionary tales. They are challenges, proving that life does not require comfort. They are proof that the universe does not need to be gentle for complexity to emerge. They are stages upon which evolution performs its most impressive acts, and this, in turn, informs our search for life. Traditional searches for exoplanets focus on the habitable zone, the region around a star where liquid water can persist on the surface. But this may be too narrow a perspective. Life may flourish under ice, in chemical oceans, in subterranean networks, or in tidal pools invisible to telescopes. Astronomers now scan for anomalies in infrared emissions, for chemical disequilibria, for subtle signs that something unusual is occurring below the surface. Exoplanetary science is shifting from a search for Earth twins to a search for energy exploitation, where energy flows, life, and perhaps intelligence, may be present. And as we imagine life surviving under unimaginable conditions, the drama escalates, because these discoveries force humanity to reconsider its own trajectory. If life can endure extremes, then intelligent life may also survive conditions we cannot yet create or control. Perhaps adaptability, resilience, and long-term thinking are as important as technology. Perhaps survival in the cosmos requires lessons in patience, endurance, and observation as much as scientific advancement. In this sense, the universe challenges us. It shows us that extremes are not obstacles, but opportunities. It demands that we expand our understanding of what life is, what intelligence is, and what it can become. And the stakes for humanity become personal, because the more we understand the extremity of other worlds, the more we appreciate the fragility of our own. Our stability is a privilege, not a guarantee. Our environment is not a birthright, but a temporary alignment of forces, and if we fail to safeguard it, if we fail to cultivate resilience in our species, the extremes of the universe will eventually test us as well. This realization acts as a turning point in the narrative. The story shifts from observation to reflection, from wonder to responsibility, from curiosity to existential awareness. Uninhabitable worlds are no longer distant oddities, they are mirrors. They force humanity to see both our potential and our limitations. They suggest that survival may depend less on the technology we build and more on the perspective we adopt. And yet, even in the harshest environments, life finds a way. This sets the stage for the next escalation. If we can imagine life surviving under lava oceans, glass rains, tidal locking, and crushing pressures, then the universe becomes less hostile, not gentle, not forgiving, simply challenging. Challenges require solutions. Solutions require ingenuity. Ingenuity requires observation, adaptation, and persistence. The rising action, then, becomes a lesson in possibility. Extreme planets are not dead ends. They are test beds. They are proof that the universe is never simple, but it is always inventive. And for humanity, the message is clear. The story of life is not confined to comfortable zones. The story of intelligence is not limited by initial conditions, and the story of survival may depend on embracing extremes rather than fearing them. As our telescopes continue to catalog thousands of new worlds, the same pattern repeats. For every burning lava planet, there is a hidden ocean. For every glass storm, there is a chemical refuge. For every violent flare, there is a magnetic shield. And within those refuges, life endures. The universe, it seems, is both ruthless and creative. It tests, it challenges, it hides its treasures, but it does not destroy them without leaving opportunity in the shadows. This perspective brings clarity, but also anticipation, because if life thrives under extremes, then intelligence may also emerge in unexpected places. Civilizations may arise where we least expect them, and they may do so in ways we cannot immediately recognize. Extreme worlds, once symbols of despair, become symbols of possibility. They teach us that survival is not about comfort, but about adaptation. They show that endurance can be more significant than abundance, that persistence may matter more than perfection. And in this realization, the universe feels simultaneously daunting and hopeful. It is daunting because the rules are not forgiving. It is hopeful because life, in all its stubborn ingenuity, is rarely constrained entirely by the limits we perceive. As we continue to explore the extremes of exoplanets, a pattern emerges that forces humanity to reconsider not only life's adaptability, but the very nature of intelligence itself. Every lava world, every iron planet, every frozen orb and tidal lock nightmare teaches us something new. Resilience is a prerequisite for complexity, and stability is a rare commodity. Yet, in these extremes, life not only survives, it adapts, innovates, and persists. Consider the implications of planets with vast, unbroken oceans beneath kilometers of ice. Europa and Enceladus are our closest analogs, but when we extrapolate to exoplanets, the scales become almost unimaginable. Oceans hundreds of kilometers deep, insulated from radiation by thick ice, warmed by tidal flexing or internal radioactivity, could host ecosystems capable of existing for billions of years without sunlight. Chemosynthetic life, thriving on chemical gradients and thermal energy, may form dense webs of interdependent organisms, creating a complexity that rivals surface ecosystems on Earth. But unlike Earth, this complexity is hidden. It is invisible to telescopes, invisible to infrared sensors, and largely invisible to us. These subsurface worlds challenge our assumptions. Life does not need visibility. Life needs energy and gradients. Where those exist, even in extreme isolation, life finds a way. Now, add moons to the equation. Many of these subsurface habitats exist not on planets, but on moons orbiting gas giants. Tidal forces flex the interiors, creating heat and motion where otherwise frozen silence would prevail. Moons like these may be more habitable than planets directly exposed to their stars. But the challenge is subtle. While tidal heating creates liquid water, it also generates high radiation levels from the parent planet's magnetosphere, creating selective pressures that push life toward resilience. Microbial life may thrive, but evolution is being accelerated by adversity, and if complexity arises, it may do so in a way that is fundamentally different from life on Earth, optimized for extremes, for isolation, for endurance without notice. And then there are rogue planets, worlds wandering the interstellar void without any host star, once thought entirely lifeless. Recent models suggest that geothermal heat from radioactive decay can sustain subsurface oceans for billions of years. Life, if it emerges there, exists in total darkness. It knows nothing of seasons, nothing of day and night. Its entire world is energy sourced from within, shielded from stellar influence. Such life is as alien as it gets, but it exists, demonstrating a universal principle. Wherever there is energy to exploit, life can persist. The rising action escalates further when we consider extreme atmospheres. On super-Earths or mini-Neptunes, pressures can reach hundreds of bars. Atmospheres may be rich in exotic gases, and surfaces may be molten or metallic. Life, if it exists, must adapt not just chemically, but physically. It must evolve ways to handle crushing gravity, corrosive chemical exposure, and volatile weather patterns. And yet, these extreme environments are not static. They are processes, dynamic, turbulent, and alive in their own right. Organisms may migrate vertically, flow on turbulent atmospheres, or anchor to resilient substrates. Each adaptation is a response to chaos, a demonstration that life is capable of surviving environments that would appear instantly lethal to humans. Here lies a critical turning point. The universe is not hostile because it seeks to destroy. It is indifferent, but it is patterned. Physics provides challenges, and those challenges, if navigated successfully, enable resilience and ingenuity. Extreme worlds are not barren, they are formative. They are the crucibles in which adaptation is tested. Life may not become complex in every instance, but the potential is always present. Survival in these contexts requires observation, anticipation, and innovation, the very qualities that underpin intelligence. Extreme planets may suppress technological civilization, but they also forge the traits necessary to reach it. And when intelligence does emerge, the implications are profound. A species evolving on a tidally locked planet, surviving in the narrow twilight band, or beneath an ice crust heated by tidal forces, must solve problems of energy management, environmental control, and long-term planning far earlier than humanity ever had to. Civilization under such conditions would prioritize patience, foresight, and risk management, cooperation and stability, not just moral choices. They are survival imperatives. Technology, once achievable, must be durable and adaptive, designed to persist under conditions we cannot fully anticipate. Intelligence becomes inseparable from resilience. But there is another layer. Consider how visibility changes the stakes. On Earth, our biosphere is partially visible. Oxygen, methane, and carbon dioxide create atmospheric fingerprints detectable from afar. On subsurface or extreme worlds, this is not the case. Life can thrive without ever revealing its presence. For intelligence, this introduces a strategic consideration. The more energy and technology a civilization uses, the more detectable it becomes. In extreme environments, energy may be scarce, and caution may be encoded into the very nature of survival. Perhaps advanced civilizations in harsh worlds have learned to remain quiet, to conserve, and to hide their progress from external forces. In a universe filled with extremes, stealth may be as essential as adaptation. This reframing of visibility and energy use intensifies our understanding of uninhabitable worlds. They are not merely places where life struggles. They are arenas that shape the trajectories of evolution and intelligence. Harsh conditions filter for endurance, challenge, and ingenuity. They sculpt biology and, potentially, civilization. They may delay the emergence of technological species, but when such species do arise, they are extraordinary by necessity. Their intelligence is molded by adversity, their survival strategies honed under the most rigorous constraints imaginable. And as we catalog these worlds, a pattern emerges that is both humbling and provocative. The galaxy is not a gentle nursery for life. It is a complex, dynamic environment filled with energy, chaos, and hidden opportunity. Life persists in niches we might never consider habitable. Intelligence may arise in places that defy our imagination, and yet, the vast majority of planets remain uninhabitable from our perspective. Molten surfaces, glass storms, frozen wastelands. These extremes highlight the fragility of our own home. Earth is an extraordinary anomaly, stable enough to allow complex life and intelligence to emerge. We are privileged not only by habitability, but by timing, circumstance, and resilience. The rising action peaks when we consider what these discoveries mean for humanity's future. If life can persist under such extremes, then intelligence, if it survives long enough, may transcend environmental limits entirely. Civilizations could evolve on worlds we consider inhospitable, mastering energy extraction, resource management, and environmental engineering far beyond our current capabilities. We may find ourselves observing not only life, but intelligence that has learned to navigate chaos, to exploit extremes, and to endure in isolation. The narrative of Uninhabitable Worlds transforms, from a story of limitation to a story of potential, from despair to preparation, from observation to anticipation, and finally, the crescendo of understanding begins to coalesce. Extreme planets are not merely oddities in a catalog. They are the universe's lessons about survival, about adaptation, about intelligence under pressure. They teach that life is persistent, that intelligence is conditioned by challenge, and that the cosmos rewards ingenuity over comfort. They warn that stability is rare and that visibility carries risk. They reveal that the rarest and most precious outcome, durable intelligence, may require navigating extremes, not avoiding them, and they prepare us for the final revelation. The universe is not barren, but it is indifferent, and in that indifference lies both peril and possibility. The payoff of our journey through uninhabitable worlds comes not from discovery alone, but from understanding what these extremes teach us about life, intelligence, and the fragile arc of civilization. Every lava world, glass storm, and frozen wasteland is a testament to the universe's indifference, and yet, in that indifference, there is a profound lesson. survival, adaptability, and insight matter more than abundance, comfort, or visibility. We begin with life itself, across countless extreme exoplanets. From the tidal-locked worlds to subsurface oceans on distant moons, we see that life is not fragile. It is stubborn, opportunistic, and remarkably inventive. Energy, not sunlight, can drive ecosystems. Gravity, pressure, and radiation, not barriers, but challenges to be overcome. Chemosynthetic webs, tidal heating, and geothermal gradients provide sustenance where surface life would perish. Life exists where we do not expect it, in niches invisible to our telescopes and undetectable by conventional signals. It persists quietly, patiently, enduring conditions that would obliterate human ambition in moments. But the real payoff emerges when we consider intelligence. Unlike microbial survival, intelligence requires not just persistence, but continuity. It requires stable conditions long enough for information to accumulate, for problem-solving to become cumulative, and for technology to emerge. The very extremes that seem hostile, fluctuating climates, tidal forces, intense radiation, can shape intelligence in ways we rarely consider. Survival under these conditions selects for foresight, patience, cooperation, and ingenuity. A species evolving on a world of constant challenge may be small, hidden, and slow, but it is disciplined, resilient, and capable of extraordinary adaptation. This leads to an unsettling but illuminating possibility. Perhaps advanced civilizations are not the noisy, galaxy-spanning empires imagined in science fiction. Perhaps they are quiet, careful, and deeply adapted to extremes. They may conserve energy, avoid unnecessary risk, and remain invisible, not from malice, but from necessity. If extreme planets teach anything, it is that the cosmos favors subtlety over spectacle. Life survives, intelligence emerges, but it does so with caution and respect for the relentless pressures of its environment. Here, the lessons for humanity crystallize. The Earth is a rare refuge of stability. Our civilization has flourished in a narrow window where climates are moderate, resources are abundant, and geophysical processes provide continuity. But uninhabitable worlds remind us that this window is neither guaranteed nor permanent. The survival of intelligent life is never automatic. It requires planning, restraint, and adaptation to challenges beyond our immediate perception. Civilization is fragile, and intelligence can be ephemeral if it ignores the lessons encoded in the cosmos. Furthermore, these worlds redefine our expectations of exploration and observation. Life may be abundant, but it may not announce itself. The universe could be teeming with intelligent species thriving in subterranean oceans, tidal zones, or insulated niches that shield them from detection. The silence we perceive in the cosmos is not evidence of absence. It is evidence of subtle survival strategies perfected over millions or billions of years. In this context, the search for life must expand beyond the familiar. We must look not only for Earth-like conditions, but for energy gradients, chemical disequilibria, and hidden refuges. The payoff extends beyond the scientific. It is existential. Extreme worlds teach humility. They remind us that survival, ingenuity, and foresight are the true measures of a civilization, not wealth, size, or audibility. They compel us to consider the long-term consequences of our choices, our technologies, and our stewardship of the planet. They frame humanity's story within a broader cosmic narrative, revealing both our rarity and our potential. If life persists against extremes, and intelligence emerges under pressure, then the next step is ours, to adapt, endure, and aspire without arrogance or complacency. In practical terms, the lessons are striking. Energy is finite, stability is temporary, and visibility can be risky. Civilizations that endure may be those that balance ambition with caution, expansion with sustainability, and exploration with foresight. The universe, in its indifference, rewards none but those capable of navigating extremes with wisdom. For humanity, this is both caution and inspiration. It is a call to engineer not just for growth, but for resilience, to pursue knowledge not only for curiosity, but for survival, and to recognize that true longevity requires aligning with the deep, persistent patterns of nature, rather than attempting to bend them recklessly. Moreover, extreme worlds reshape our philosophical perspective. They force us to decouple survival from comfort, intelligence from dominance, and visibility from value. Life on a rogue planet or beneath a frozen ocean does not boast its achievements. It does not demand recognition, yet it persists, adapts, and evolves. Intelligence under extreme pressures may operate without spectacle, without conquest, without broadcasting its existence. This challenges anthropocentric assumptions. The cosmos is not obligated to notice us, but it does model what endurance and ingenuity can achieve. As we synthesize these insights, the narrative arc comes full circle, from discovery to rising action, from conflict to comeback, and finally to payoff. The story of Uninhabitable Worlds offers both caution and inspiration. They illustrate the fragility of habitability, the subtlety of survival, and the enduring power of adaptation. They teach that extremes are not the enemies of life, but its crucibles. They reveal that intelligence is not inevitable, but attainable, provided it navigates challenges with foresight and care. And they remind us that the universe, indifferent as it is, rewards those who endure and innovate over those who seek immediate triumph or recognition. Finally, there is a poetic resonance to these lessons. In the silent oceans beneath icy crusts, in the turbulent atmospheres of molten planets, in the invisible ecosystems of rogue worlds, life and intelligence persist without witness, without applause, and often without ever being seen. They are testimonies to endurance, to adaptability, and to the quiet brilliance of evolution, and humanity, in observing and understanding them, gains a rare opportunity to learn, to reflect, and to act with a consciousness shaped not by complacency, but by the magnitude of what the universe demands for survival. The true payoff, then, is perspective. Uninhabitable worlds are not barren. They are laboratories of survival, theaters of adaptation, and arenas of intelligence tested under conditions that push the limits of possibility. They show us what life can endure, what intelligence can achieve, and what civilizations must master to persist. And they offer a profound, almost philosophical insight. The universe does not guarantee comfort, success, or visibility. It only guarantees opportunity for those who observe, adapt, and persist. In the end, the story of extreme planets is a story about life's stubborn creativity, intelligence's measured emergence, and humanity's potential responsibility. It reframes our understanding of what it means to exist in the cosmos. Survival is a challenge, adaptation is a necessity, and endurance is a triumph. The payoff is clear. In observing worlds that defy habitability, we learn how to navigate our own fragile existence, how to cultivate intelligence that can endure, and how to aspire toward futures shaped by both insight and resilience. The universe is extreme, but life is remarkable. And in that tension lies the ultimate lesson, one that humanity cannot afford to ignore. As the story of extreme worlds draws to a close, we find ourselves standing at a unique crossroads, between observation and reflection, between knowledge and understanding. For billions of years, the universe has been indifferent to life, intelligence, and ambition. It has forged planets of molten rock, oceans trapped beneath ice, skies filled with corrosive rain, and atmospheres that crush, scald, or freeze. These worlds have existed silently, without purpose or intent, indifferent to the questions of observers light years away. And yet, from this indifference, life, stubborn, ingenious, and resilient, has emerged time and again. The lesson is clear. Life does not wait for ideal conditions. It does not demand comfort. It seizes opportunity wherever energy flows and gradients exist. And when extreme conditions are navigated successfully, they produce adaptation, innovation, and persistence, the very foundations of intelligence. A species that can endure a planet of constant storms, of shifting tectonics, of tidal heating and ice-crusted oceans, is a species that understands patience, strategy, and resilience. These traits, honed under duress, may be the essential prerequisites for any civilization seeking longevity. As humans, we have long defined life by our own standards: liquid water on the surface, oxygen in the atmosphere, temperate climates, and energy derived from sunlight. Yet extreme worlds force us to confront a more expansive reality. Life does not need to resemble Earth. Intelligence does not need to be audible or visible. The universe is filled with niches we have yet to imagine, teeming with potential forms of complexity and awareness that exist quietly beneath layers of ice, oceans, or rock. This quiet entrance reshapes our perception of cosmic significance. The silence of the universe is not proof of emptiness. It is a reflection of subtlety. Life and intelligence can thrive without broadcasting, without altering their environments visibly, without drawing attention. Survival, not spectacle, is the highest achievement. In this sense, the extreme worlds we once feared as uninhabitable, not obstacles, they are proof of possibility, mirrors showing us the traits necessary to persist. For humanity, the implications are profound. Our civilization exists in a rare window of stability, yet we are aware that this stability is fragile. Earth's conditions, abundant water, moderate climate, protective magnetic field, are exceptional. The universe teaches that longevity, for life or intelligence, is never guaranteed. We must cultivate resilience, foresight, and adaptability if we hope to endure in the cosmic context. And we must recognize that visibility carries risk. Our growth, energy use, and technological footprint may render us conspicuous in ways we do not yet fully understand. Yet there is hope embedded in these lessons. Extreme worlds show that adversity fosters ingenuity. Life persists where we imagine impossibility. Intelligence emerges under pressure, and when it does, it carries the potential to surpass limitations that would otherwise seem insurmountable. Humanity, by studying these worlds, learns not just about alien life, but about itself, its potential, its fragility, and the long arc of civilization it seeks to navigate. In the end, extreme exoplanets are more than scientific curiosities, they are guides. They remind us that survival and intelligence are processes, not destinations, that adaptability matters more than abundance, that patience and strategy may outweigh ambition and speed, that the universe is indifferent, yet full of opportunities for those capable of observing, learning, and enduring. And as we close the chapter on the uninhabitable worlds, we are left with a sense of perspective both humbling and inspiring. Life, wherever it emerges, finds a way. Intelligence, wherever it arises, is tempered by the conditions that shaped it. Humanity, in turn, is challenged to match this resilience, to understand that the cosmos does not owe us comfort, clarity, or attention. It only offers the chance to persist, to adapt, and to aspire, quietly, patiently, and creatively. In that quiet, patient striving, we may discover the truest measure of progress, not dominance, not expansion, not visibility, but endurance. The universe will continue to forge extremes, to test life against impossible odds, and to reward those capable of navigating its relentless challenges. Humanity has the opportunity to join this continuum, to learn from worlds that at first seemed uninhabitable, and to recognize that the rarest achievement may not be intelligence itself, but wisdom, the understanding of how to endure, how to adapt, and how to persist in a universe that offers no guarantees. And so, when we look at distant planets of molten rock, frozen oceans, iron rain, or violent storms, we are not merely observing danger, we are seeing potential, the potential for life to adapt, for intelligence to emerge, and for civilizations to endure. We are seeing mirrors of ourselves, fragile, ambitious, yet capable of extraordinary resilience. In the end, the uninhabitable worlds teach the most profound lesson of all. The universe is extreme, life is stubborn, intelligence is rare, and survival, true survival, requires not only adaptation, but wisdom.